All right. Welcome, everybody. Let's go ahead and get started. So I don't have any announcements for today. So I'm just going to go ahead and turn the introductions over to Professor Pavel Nadolsky. So he just sat down. Sorry, man.
Yes. So hello, everyone. So today I welcome Professor Aurore Courtoy from National Autonomous University of Mexico. The seminar today is dedicated to a very interesting topic, the physics of the Electron-Ion Collider. Now, Aurore is an expert on the various aspects of non-perturbative quantum chromodynamics. Aurore got her PhD in 2009 in University of Valencia in Spain. And then she had a number of follow-up positions at Pavia, Liège, together with Frascati and Mexico City, before she came to our side of the Atlantic Ocean, where we initiating a new major project called the Electron-Ion Collider, which will study multiple aspects of the three-dimensional structure of the hadrons. So today we'll have a review talk dedicated to this very rapidly developing area. And for those who are interested, on Wednesday, we will have a follow-up recitation at 3 to 5 p.m. in the room 202. So we can discuss further details, especially any questions that we may have about the theory that will be discussed. With this, I welcome Aurore.
Thank you.
Her talk.
Thank you so much.
Let's give her a proper welcome.
Okay. Okay, thank you very much. So I will talk about one aspect of the EIC, which is a huge program. So I can't cover everything, also because I'm not an expert on everything, but I will talk especially on quark-gluon correlations.
Okay.
Okay.
I'm going to turn off the beeping sounds too. Okay.
Okay, wonderful. I think we're all used to the Zoom sound now. Okay. Okay, so let me just, that's the first in-person talk in many years. So let's see if I can remember how it works. Okay, so I copied this from the EIC webpage, and there's this fundamental quest that we have, which basically consists in how can we break down the quest to understand the Hadron structure. And if you go on the webpage of the EIC, you will see there are many interesting points, like how do quarks and gluon make up for the visible matter of the universe, precision 3D imaging of nucleons, solving the Proton spin puzzle, the emergence of hadronic mass, quark-gluon confinement, and all those things, right? And I will talk just about, well, I won't talk about everything, but I will give my 2 cents on some of those topics, but not everything, okay? And so those that are highlighted here actually can find answers or a partial answer or hints of answers through the study of Parton distribution functions, which I guess here you'll know because you have all this CTEC members, so you must know a lot about PDFs, but I will just review a few things about PDFs. And in particular, the hadron properties I've mentioned before, like the spin, the mass, most of them involve higher twist distributions. And what is really interesting is that those properties are accessible through manifestation of QCD at low energy, okay? Which means that the hadron structure beyond leading twists, which I will mention, I will explain what it is in a few minutes, is relevant and accessible. So this talk will have these 3 main points, which will be what are higher twist distribution functions, what information do they encapsulate, and what can we learn from low energy experiment to higher Q square, which, as we will see, EIC for us is higher Q square, okay? It's really high for higher twist. Okay, so this is the picture of the degrees of freedom of the proton. So at low energy, you can consider it as a hadron as the degree of freedom. And as you increase the resolution, the Q square, you will see more and more inside the proton. And at low energies, you will consider that you have this constituent like quarks. And at high energy, very high energy, you would have all those pairs and gluons. And this is, of course, paired to the behavior of alpha strong, okay? And what we would like to study at really low energy, like a Jefferson lab, for example, would be this kind of energies here, mid-range energies. And the EIC will help us cover a bit more. So the idea of that is that you've heard about this EIC, the glue that binds us all. So what is that glue that binds us all? So perhaps part of the answer is actually gluon at low energies. So, you know, gluon has radiation at high energies, but even a lower energy, you would have gluons coming as the dynamics of QCD. So how can we access that information? There are many observables, but in this talk, I will talk a bit about the quark-gluon interactions. Okay, so how can we go to these quark-gluon interactions in PDFs? So that will be PDFs at leading twist. This is the one that everybody knows, the most polarized PDF. Then you have two other PDFs at leading twist, which are the helicity, that gives you the spin, and transversity, which gives you something similar to the spin, but in the transverse direction, okay? And all three are complementary and really interesting. And the most famous one is the polarized PDF. And we know a bit less about helicity and transversity, but they still are leading twist PDFs, okay? So they are defined on the icon. So if you take the plus component, and you know that Birken X is the fraction of a momentum that carry the active quarks, and you can relate, you can plug them into observables, thanks to factorization theorems, and then you know the evolution too, right? So now if you want to go a bit further in the development, then you would have like on decomposition. So you would see they have this leading twist here. Let me just show them. Leading twist PDFs, okay? So the unpolarized, the helicity and transversity here. But as you can see, you can have transverse and negative components of the icon too, which is gonna give you twist 3 that are suppressed like m over p plus, where p plus is the direction of the proton, the momentum in the proton, and then you would have the twist 4, okay? And all those guys are suppressed like m over p plus or m square over p plus square. Okay, so it seems that if you go to really high energy, so p plus is like Q, you go really high energy, those guys will just disappear, okay? But if you consider lower energies, they will kind of matter, okay? So just one slide of terminology of the zoo of distribution functions. So I mentioned PDFs, and they are what they call the collinear PDFs, the integrated PDF, or whatever you want to call them, and they depend on X, Bjorken, and Q squared, okay? But I will just mention a few things in the talk too about GPDs and TMDs. And so if you want to take this image of the proton that goes really fast in one direction, you would have this transverse plane. And then you would see, don't put your eye there, but you would see this image here. And X corresponds to this longitudinal momentum of the proton, of the quark, okay? But then you want to add dimensions. And if you want to add dimensions, you could do it two ways, or you can combine all those two ways. One way is to add the transverse momentum on the plane, which gives you TMDs, so it will be 3D. The other way is to go to GPDs when you have momentum transfer, which gives you like the impact parameter here, okay? And so GPDs are three-dimensional distributions, just like TMDs, just different representations, okay? Excuse me? Yes, sorry. TMD is transverse momentum distribution, and GPD is generalized. So we know that they're not so general, but it's called generalized pattern distribution. Yes. Yes, exactly. So I didn't put the picture here, but if you combine this one and this one, you would have a 5-dimension. And yeah, but those one are not accessible to experiments yet, but okay. And I don't think I will mention them, but okay. So PDF, the one I'm going to talk about, and I will mention a few things about TMDs and about GPDs. And then of course, if you integrate PDFs over X, you get the charges. And if you integrate GPDs over X, you get form factors, which depend only on the transverse momentum square. And you can complete the cube, but the other ones are just more exotic things. But that's the cube of the zoo of functions. Okay, so let's go back to collinear PDFs. Okay, so still the unpolarized helicity and transversity, just to show you here. So that's a plot of X and Q square ranges. So they have some existing data, and then you would see the EIC here is shown for helicity and transversity to give you an idea of what will be covered. But what I would like you to see here is that, so that's 1, okay? So there's a cut of 1 Q square, Q square by 1 here, okay? And then what you can see is that for some experiments, the ratio m over q is not that small, okay? So especially you see these ranges, right? So sometimes what would happen if when you make your analysis, you would have some contamination coming from m over q, or what you can do too is that you can define some asymmetries to get sensitive to this m over q term, right? So there are two ways. So what do I want to say by that is that you can see them as contamination or spurious terms, like you have here. I guess you're familiar with CJ15, and they have a lower cut, so they would include more data in that closer to the q square equal 1. And so they have to take into account what they call HT, which is higher twist terms, and here would be by q square, right? And so they have to fit them to get to their fit. They have to take into account those corrections. And so that's the way you see the impact of higher twist. And also you can see, if you want to go further, higher twist, as I will explain in this talk, have a lot of physical content, and they can also play a role in fulfilling duality, for example. But you can also see them as, okay, depending on the function you want to access, you can see that they also have genuine effects. And that genuine effects is really non-perturbative. For example, in the analysis by the JAM collaboration, they analyze the helicity, which is just this one here. That's this set of data here. And then they know they're going to have also a twist tree. And so they fit this function here. And you can see, so that would be the helicity they get. And then they also have the twist tree function. So there's two sides. So if you don't know much, you put them as a contamination, and then you try to do something with them. And then you can try to go further, as we've done with the JLab and we do with the IC, and try to extract them. Okay? So what do I call genuine effects? And that's the interesting part of so I will talk about, okay, I think I mentioned it here. So GT that I mentioned before is the sum of the helicity and G2, which is the twist tree part. And so if you analyze from the matrix element, and you can work out with the equation of motions, you can realize that as a relation of G2 can be reduced to a twist 2 PDF plus another term, okay? But if you take this reduction, it's called the Van der Waals relation. And what we call the Van der Waals approximation is basically just that part here. So you can, in principle, know part of the twist tree thanks to the twist 2 PDF. But if you take into account the genuine effects, then you would have the quark-gluon quark correlation here in this tilde term. So the tilde term is actually the interesting part of G2 from my point of view, okay? And you can just work out the equation of motions, and you will find that you have the quark-gluon quark correlation here. Another aspect too is that since we are on the light cone, there are some what we call singularities, so delta x. So at the origin, at x equals 0, you will find something like this in some models, and it can also be found through the equation of motions. So you would have the same equation as this one here, but in some models, you would find the delta function for the case of G2, right? And some others, we always have this singularity here. So it means that they are what you call these zero mode effects. Okay, so what I want to say here is that we know part of this function, but we don't know the rest. Okay, so how do we know that those other effects are not zero? They are non-zero. So the first thing that people have done is said, okay, we work in this approximation here, and we just keep the twist 2 part. So we know G1, we can get G2. And so that's what people have done for a long time. And it could be worked out through experiments, actually. And there are some studies, about 10 years ago, a bit more, that suggested that it was not enough. So if you compare the Van der Waals reduction here, approximation on G1 or G2, you realize that you need something else, right? So this delta here, which is the blue curve here, is non-zero, which suggests that you need the G tilde. So there are actually quark-gluon quark interaction here. So the question was how to access it, right? So the good thing about G2 is that it is accessible to DIS, but here we'll talk about the EIC. But let me just mention here, JLab 12, that triangle here that you can see. So this is something from the yellow report of of the EIC. That's for polarized EIS data. And this is something for the white paper on second interaction region for the EIC, which is being written right now. Okay. So what you can see is that what is covered from known experiments will be this region here. So the EIC at really high center of mass would be in that region. Okay. And if you have a lower center of mass, you would cover a slightly lower Q value and slightly larger X value, right? Which would be ideal for higher twist, actually. So you can see here what is expected from this second interaction region, for example. Okay, so it's like a smallish Q square, and smallish X, but not too small X. We don't need to be too small in X. And so I will try to discuss the complementarity of this data. Okay, so why are higher twists so important? And what do we know about them now, right? And what do we need to do to know better? Okay, so that's the interesting part. Okay, so higher twists can contain quark-gluon quark correlations, quark mass term that I've not mentioned before, but they also have a quark because use the equation of motion, so you would have a mass term for the quarks, and they can contain this singularity of this zero mode, if you like. And what is also really interesting is that many properties of the hadrons are related to that. For example, if you take the proton spin, there's a component that comes from the quark-gluon quark correlations in GPDs. If you take the proton mass, there's a singularity in the scalar PDF. And beyond that, there are this discussion about universality of PDFs, especially when we talk about Sievers and Schusterman effects. So this is TMD, and this is more complex, but there's a lot of discussion about that. Let's keep it simple for today, okay? So proton spin, quark-gluon quark correlation. So a few years ago, there was this discussion about the orbital angular momentum, and there are two definitions, right? So you want to understand which is the spin of the quarks, the contribution from the gluon, and the OAM, right? And as you can see, this thing, there was always part of the pie that was in disagreement with everybody, right? And so is this JM is for Jaffe Manohar, and the one is G. And it was shown that this piece of the pie is nothing else than quark-gluon quark correlation in GPDs. So it means it's higher twist. And why is it so helpful is that we can now try to fix observables. What would be the observables to understand that, right? So we know what is here, right? So that's interesting. But now the discussion moved to the proton mass. And so the proton mass is like a hot topic right now, especially with Compass plus and the EIC. And so what is the thing about the proton mass? Well, that's kind of a propaganda. Of course, the SAMs are kind of, you take it like just as a SAM, okay? So if you take the Higgs mechanism, you expect to have, that's what we always say, that the current quark mass at a given scale, I think that's about 2 GeV, don't make up for all the mass that you expect in the proton. So the mass of the proton means that 99% comes from QCD, right? And how, that's a big thing. We don't really know, but the question now is, how can you decompose it? So you have a big question, how do you generate that mass? And you make it like a slightly easier question, how can I compose the mass, right? And that's how we decompose the mass. There are also 2 different masses, decomposition. There's the G and the lossy one. And so you would have like about 1 GeV here, and you decompose it to mass of the quark, the trace anomaly, and the energy of quarks and gluons, okay? And so just to make it a bit more clear, so this energy is related to the moment of the unpolarized PDFs, and the quark mass is the sigma terms, okay? And this one is it will be the condensate of gluons, okay? So what can we access from experiments that give us answer to that, right? So this, I think here you have CTEC can give you that, okay? So that's wonderful. The trace anomaly is the one that nobody knows exactly how to get to, but what we also need to get from experiments or from other approaches are the sigma terms. And the sigma terms are what I'm going to talk about now, okay? So you have this mass decomposition. So the sigma terms are just like a condensate of quarks, but between proton states, not between the vacuum, right? So they go on top of that. And so you have the sigma by nucleon, where you have the up and the down, and the other strange. And so those have been determined from nucleon data on the lattice as well. Okay, so they're kind of known, but not from experiments. There's no phenomenological, well, here if you like, but there's a lot of process. But what is interesting here is that they are related to the PDF E of X by some rules. So if you take this PDF, that's scalar PDF as shown at the beginning, you will have the sigma terms. Okay, so that's really interesting because that PDF is related to the mass of the proton. Okay, so now get to that PDF. Remember I said that you can have this singular term or local term. Okay, so that would be a delta here. You would have the quark-gluon quark interaction, and you also have a mass term, right? So that PDF has everything, all 3 terms. And now the question is that, okay, how can we access this information? So we would like to have all this information, and we would like to understand the role of each of the terms, but first to get to the PDF. Okay, so how do we get to the PDF? So this one is scalar, so you cannot access it in DIS, in inclusive DIS. You need to go to semi-inclusive DIS. So how do we do that? So once you add, so in semi-inclusive, you will detect, say, a pion or pair of pion or kaons or other things. So you would have the PDF or the quark correlator here, but you also have a fragmentation part, right? And so the cross section would be a product of the quark PDF or TMD, okay, and the fragmentation part. And this allows you to have much more structures because you would have, in that case, you have, so the transverse momentum, which is KT, and you would have many things. So if you want to go to higher twist, you can decompose. So usually you would have this correlator here as twist 2 PDFs, but you can also have m over p plus times the twist 3 PDFs, okay? And same on the top, right? You could also have the same thing for the fragmentation here. But on top of that, since it's already included here too, but since those twist 3 PDF contain a quark-gluon quark interaction, you can also have those kind of suppression here. So this phi A contains the gluon too, right? And so you can work out how to write the mini asymmetries. So you would have the cross sections. You can define angles and asymmetries, and you would have a lot of different asymmetries that will give you access to twist 3 PDFs. Okay, and actually they were measured by Hermes in class, many of them, and they are not exactly 0. Not all of them. Some are not small, and some are not. Right. The huge problem with this is a theory will be more like a TMD approach. And so the problem with that is that you have many functions. And what happened is that you have so many terms that it's all very intertwined, right? So there was an alternative to that was so proposed for the transversity actually, is to go to semi-inclusive DIS for dihedron or dihedron cities, if you like. So here you would just add one hadron, but here you would just detect pair of pions. So you would have pion pairs here. So that would be the same kind of diagrams. And in that case, the good thing is that you don't have to be in the TMD framework, but you have in collinear framework, okay? And that's what has been used for the transversity extraction as well. And so in that case, you would have symmetries of that type, in which you would have a twist 3 PDF times a twist 2 fermentation function, and a twist 2 PDFs times a twist 3 fermentation function, okay? And that's how we're gonna access this scalar PDF. And so the scalar PDF would be in that asymmetry. You can see it here. And I'm gonna talk about that. Okay, so those are the whole data we have for this scalar PDF. So the funny part is that, so class is Jefferson Lab. So this was the last paper of class with 6 GeV, and that was the first paper of class with 12 GeV. And as you can see, they are published in the same, in the same issue of PRL. So but the funny thing is that it was about the same asymmetry, right? And that was pretty cool. So we got 3 points from class and 12 points for class 12. So the first thing I want to mention is that only class 12 shows non-zero, clear non-zero twist 3 asymmetry, where it's not really clear from class. And the shortcoming is that there's only one target, which is a proton target. So we can just access this combination of U and D, okay? Okay, so the great news is that it's non-vanishing. but we don't know if it comes from the fragmentation part or from the PDF part. And so we're going to study this slightly. Okay, so we just have this thing. Okay, so how do we access this twist-tree PDF? We work out this asymmetry. And so we know the leading twist dihedral fragmentation function that we have here. So this, how it fragments into two pions. We work that out. We know it from other analysis that we had from the transversity part. But then we have to see what you do with this other term. So that would be the unpolarized PDF and the twist-tree, Janine twist-tree fragmentation part. And so there's not much we know about it. This was just one model talking about this kind of things. But there are other symmetries from COMPASS that help us do so, right? So we work that out. And this is very preliminary. So it's been there for 7 years. We've worked the analysis again. And so we make two scenarios. I'm just going to discuss about the results. And that will be the combination of 4U minus ED divided by 9. So that's a combination of valence PDFs. And so what I want you to see here is that we have two approximations, two different scenarios. And we just want to know how much is it different from 0? To which confidence level is it different from 0, right? And so you can see that class is not that much, well, it could be 0, it's compatible with 0, but class 12 is not so much, right? So that's wonderful. So that will be this combination that we have here. So, and I just want to mention here that this is a full uncertainty, right? So that will be the 100% of, we use the bootstrap here technique to get that. It's 100% of the error band. So the good news is, since that from class 12, we probably have non-zero combination of this E of X, right? And that will be wonderful. We're gonna finish the analysis pretty soon, but that's pretty good news because we can access this PDF to get information about the mass, about the quark-gluon, but not everything at the same time, right? Okay. So how do we know about universality of non-perturbative functions? So there are many things to say here about all this framework of dihedron or even TMDs. Is that first it's all to leading order, okay? And there are not many, when I talk about global fits, they're not really global fits, right? So those fragmentation function have been extracted from E plus E minus, and they've been used in series, okay? Analysis. But they still they have to be checked or tested against other data, right? So the only thing we can do so far to check consistency, to check that if you have the data from the variables of the dihedron, when you reconstruct from the dihedron fragmentation function, you get something that is really similar, right? And that's what you can see here. So if I get the data and I reconstruct the asymmetry from my fragmentation functions that we get from E plus E minus, we get pretty consistent, okay? And so about twist 2 and twist 2 and twist 2 and twist 3 PDFs. So if we talk about twist 2, transversity is the one that we need to access to CDs as well, because it's a chiral PDF. And so this is, there are a few studies about the universality of those PDF, say in PP and CDs. But still there are global analysis of transversity that's been done from the Pavia group and JAM collaboration. And so now what about twist 3 PDFs? Are they universal? Oh, well, this is to be answered. So we don't know yet. And we hope that with the IC we're gonna have an answer. But there are examples to this TMD and what they call dynamic twist 3 relations. And what is called the Sievers function is related to the Schusterman function. So what is the goal of this extraction and why is it going to be important for the IC? So that's JLab analysis, completely class analysis. So the first question is, are genuine twist 3 effects non-zero? And I think we would say yes, up to a certain confidence level, and perhaps more for GT than for this E of X, okay? But can we access quark-gluon quark correlations or the non-perturbative information from this twist 3? So let's take this example of E of X. So that would be the combine, I combine the two things that are here. I combine them, okay? That gives me this shaded area. And so the question, and that's part of the propaganda of the IC actually, is that some non-perturbative effects are expected to actually in the smallish X region. Okay, and this is a sketch, okay? A sketch, this is not real, okay? And so I said it was a mass term. And I also said that it was a delta function. So if I take a smear delta function here, so look, 0 must be here, right? It's not 0. I expect to have a delta function and a mass term here multiplied by the unpolarized PDF here. And so what we expect is that the small x region, which is not really this tiny x region, is small, like about 10 to the minus 2, should give us some information about those non-perturbative effects. So is it really true? I wanted to insist that it's just a schematic model here to illustrate why we need the IC, because at the end, what we matter are the moments. Because those guys will give us moments. And when you have the moments, you need the whole range in X, right? And of course, the small x can play a huge role in the moment, right? And okay, there was another extraction in the TMD framework years ago. And this is all compatible with that, okay? So let's go about the EIC coverage. So this is the size of the asymmetries, as you can see. And so that's for the yellow report. So we made these projections. Since there's no fit for this E of X, we used models, two extreme models, one from a light cone quark model, another one where I just used the same thing as here. We used the mass term, okay? And we put a huge mass term. Because we are at low energies, low Q square, in principle, we're allowed to use dynamical mass here, about constituent mass, about 300 MeV, okay? And so you can see that for different configuration of the beams, that will be the lowest one, slightly higher ones. And then we didn't do it for the rest because it was just nothing to see. And you can see that you can have about 1% to 1.5% asymmetries for this configuration here. So they are non-negligible, but they are really small. And so that's the archetype of observables for this second interaction region of the IC. So what is this second interaction of the region of the IC? So that would be a plot, not really formal plot, about the coverage here, okay? So I understand that all this light scatter plot is not really observed, we don't really observe it. You should just focus on the really dense part of the plots. So that's JLab 12 that I just talked about. There will be perhaps JLab 24, but here I see this lowest configuration here will give us access to this region, right? And then when you go to higher ones, then it's just, it's wonderful for other things, right? But not for higher twist. And so the idea is to cover this range here that would correspond to a lower center of mass to complement what is going to be accessed with this configuration here. So that's what is proposed here. We see it's going to be a higher luminosity at the lower center of mass. And why is it so important? Because I haven't mentioned in this talk at all the Q-square evolution. And of course, it will matter, right? It will matter for the spin observables, for the mass observables. The mass will run. The spin moment will also run. All those PDFs will run. But that's something we still have to study. And that would be just wonderful. That would be perfect because we just need some span in Q square that we didn't have a JLab, for example. And so that would be wonderful to have a span of Q square that is not too high, not too much, but enough to start for twist 3 PDFs. So in most cases, we know the evolution equation for the genuine twist 3 part. So you know the quark-gluon quark, then you know how it evolves for the collinear ones. So for some TMDs too. And why is it going to be helpful is that, as I said, there are different parts of the PDFs, three different contributions, and evolution is going to help us disentangle and understanding each of them, right? And I understand that this is especially hot for TMD studies when they're going to have more effects to study. Okay, but this Q square is going to require this interaction region, second interaction region of the IC here. Because as you've seen for the first study, we had some asymmetries, but they're very small, right? So yeah. Okay, so talking about this multi-parton distribution at the IC, so why is it so important? And I just want to say it again. So there's going to be a larger range, not so large, but large enough for us, a large range of Q square values and smallish, but not too small X regions. So that's complementary to what we had from fixed target experiments like Hermes and Class. And also there's going to be a sandbox for factorization and evolution studies. So the golden channel here will be a fully inclusive DS with access to GT. So those are the predictions from JAM. That's taken from the yellow report. Okay, so there will be we would have proton and neutron. So we need both to have the separation, of course. And so JAM give us for now this yellow band. Okay, and that it looks like it's cut, but it means that this is only accessible with the IC. That's what they have now, and this is accessible with the IC, right? And you see how they're going to extend their analysis and how they plan to have more statistics in their analysis for GT. And the silver channel is actually semi-inclusive DIS to dihedron and perhaps to single hadron too to access the E of X, right? And so the two chosen channels are collinear observables. They are not TNDs, but there are a plethora of interesting TNDs, GPDs, and other things that are higher twist too. And there was this the sub-working group on the higher twisted DIC. Okay, so I just want to mention twist 3, E of X scalar twist 3 in Mexico. So Salvador, I hope it is connected. And it's another grad student. He said yes. Angel Miramontes is a postdoc in Michoacan, okay? And so Angel is doing the analysis of this E of X with me, and Salvador is doing the calculations in the back model, okay? And so now one of the big points and one of the reasons why I'm here is that can we do twist 3 with Fantomas? So I guess some of you have heard about Fantomas. So Fantomas is a project between UNAM and SMU. Here you can see you can fly from one to the other really fast with the car. And so Fantomas has been developed with the students. Some are here. Barada is here. They're online. Lucas is online. Ryan, Max is not connected. Max is at UNAM. She was not connected. And Pavel Naruski and myself. And it's going to help us. So now that we can extract this point by point E of X, try to parameterize this function and to get the most of it to a study of a functional form, right? So that's going to be a wonderful project. It's going to be used for other things too. That's how to study functional forms from a non-biased point of view, right? And perhaps we could use Fantomas to understand better twist 3 PDFs. Okay, let me go to the conclusions. Okay, so we have discussed the role of higher twist distribution to understand the Hadron structure, and there was a huge list from the EIC wish list. I say it's a wish list, but I really hope we're gonna go through it one day. And they contribute, for example, to precision to the imaging of nucleons, emergence of hadronic mass. That's really important. I think the mass of the proton is a really, really important thing. And as well as the proton speed puzzle, right? And of course, higher twist distributions can unveil aspects of hadron dynamics. That's a non-perturbative picture. And we still have to bridge this non-perturbative picture with the perturbative picture, of course. And they are accessible for experiments, but they still require more statistics and more analysis from the theory and the phenomenology point of view, right? And something that I did not mention, but it's there, it's wonderful, is that there are also efforts from the lattice community to get to charges, to quasi-PDFs, to PDFs, and they actually are really interested into those functions too. So that would be great to combine the efforts with the lattice. Thank you.
This is where we're going to hit the limitations. Can you switch on?
Sure. Sorry. Because they're going to be an effect. Okay.
And if you can stick to this microphone for answering questions as best you can, and I'll run this one around.
Okay, wonderful.
Yeah, because these two interfere with each other. All right, so just to check, can somebody, maybe Lucas, we'll pick on Lucas. Lucas, can you hear us online?
Yes, I can hear you.
Okay.
Wonderful. Thank you, Lucas.
Okay, so thank you very much, Aurore, and this is a very informative presentation. And now we have time for questions. And will it be okay if I have a quick question just to follow up right away? So there are two important physics questions that you mentioned. So we studied the proton, and so there are two puzzles: how the mass of the proton is formed and how the spin of the proton is formed. And you mentioned this twist three contributions contribute to both. So what's the fraction of the contribution from this high terms you expect for the proton mass, in addition to the Higgs mechanism that gives you only 10 MeV, very small fraction of the total mass, but also for the proton spin?
Okay, so do you hear me? Lucas, can you confirm that you hear me when I speak?
Yes, I can hear you as well.
Okay, thank you. Thank you, Lucas. Yes, okay, so from the proton mass, so all those masses were run. So they will always sum up to give the mass of the proton that they will run, but it's about 10% from the sigma terms, which doesn't seem to be much, but we need the sigma terms to understand the other contributions as well. And from the spin, yes, that's a good question. So I don't remember. I don't think it's a lot, and I'm not sure there are studies actually because they come from three GPDs. It's all dependent on the fits of GPDs. So maybe there are estimates on models, but I'm not sure.
But is it correct? So basically, this GPDs will contribute to the orbital angular momentum. Yes. And what is the fraction of the proton spin that comes from not from the spins of the quarks, but from the orbital angular momentum?
Well, it depends on the gluon, or the spin of the gluon. So there will be the spin. The spin of the quarks is not too much, and the spin of the gluon. So all those accessed as well to PDF. So the helicity PDFs, and depending on which, if you use DSSV and NPDF or JAM, you would have a different answer. So depending on what you have for the gluon contribution to the spin, the leftover is all OAM. So OAM.
Yeah. By like 50% maybe.
And I think a bit less, yes.
Yes, okay. Okay, let me give the mic to Fred.
Yeah, thank you again for the overview. So, for hard twist things, again, coming from the PDF side, usually, they're off in the corner and we cut on those hard so we can ignore those. But it looks like, I mean, if I saw in the slides, it looks like, for example, in EIC, you're going to have a pretty good range over X that you can really probe that. Is that right? Could you comment, make sure I understood that right?
Yeah, that's the idea. So we'd have, let me see if I have plot. Okay, so this is, I'm not sure it's just for higher twist. I think that's a general plot that has been made. I don't know exactly in which context, right? So yes, so the idea is to have X coverage and also Q square coverage, because as you can see here, the X coverage so JLab was pretty nice. So it was almost balanced region, but it was really low Q square, right? So you can still have contamination from other things, right? So the idea is to get something a bit higher. So it will be smaller hex, like 10 to the minus 2, something like that, which is not bad, and slightly better range in Q square, which means we're going to have to take into account evolution effects, which will be great. So it requires still a lot of development from our side. I think GT has it, so yeah.
Okay, other questions, Steve?
Somebody online before I jump in. Yeah, okay. So I wanted to talk a little bit about this interaction region dependence. So just out of curiosity, how recently is this particular plot showing what the EIC beam accelerator division thinks they can accomplish at the two IRs? How recently was that generated? Do you know?
So I took it from the white paper that we are writing right now. So
right now, okay.
Yes,
so that's pretty recent then.
So
okay.
There have been workshops. There was a workshop last March, I think.
Yeah.
So you can find those plots from some talks last March.
Yeah.
And I think there are other talks from Jefferson Lab, but it is like in progress, I understand. Yeah.
Yeah, no, and that makes sense. I mean, the reason I was asking was I wanted to make sure it wasn't too out of date, because I know that the accelerator physicists have continued to, their projections have continued to improve, despite what they even thought had been the rosier scenarios, maybe a year and a half ago for this as a function of center of mass energy. But it's pretty clear that IP8 IR2 is going to give you at low center of mass energy better instantaneous luminosity. So integrating data for exactly these studies will be crucial there. So flipping this over to an experimental question. You talked about the golden and the silver channels, but within those, what's your dream analysis? What's the analysis you want to see a team working on a detector experiment at IR2 pursue as quickly as possible at any of these energies?
Okay, so I'm not really involved with the whole desire to thing. It's just the higher twist. So there's a huge program which is basically what is well, it comes from the lab community. So it will be like TMDs, GPDs, and the mass decomposition is part of it. So it's all those quantities, those observables that you would have that would benefit from a lower center of mass, right? So I don't know what's going to be chosen by the whole group as the key, the flagship.
Pretend you get to dictate it. You get called in by that experiment and they say, okay, what should we measure first to address the concerns you raised in this presentation, for
From
example?
my point of view,
Yeah.
unbiased, I will go for GT.
Okay.
Because it's been there for a long time. It's inclusive DIS. But it requires a lot of efforts too. But that's the not the cleanest, but that's the one that have the path that is already taken. And then I would still go to the silver channel too.
Oh, I mean, of course, yeah. But I mean, with the
think
kinds of coverage and efficiency and acceptance that the
Well,
detector teams are talking about, inclusive is, I mean, if you can go for inclusive, go for inclusive.
I will go
right?
for inclusive, yes.
Yeah, okay, okay.
So just to continue on this line of discussion, you also pointed out that extracting twist-free contributions is actually quite difficult, even in the lowest order in QCT.
Yes.
So how can the measurements at the first interaction point help you with extraction, let's say, of EX or GT?
Okay. So there are many things.
Uh-huh.
So yeah, that's something I forgot to mention, but it can depend on you. Okay, here we go. So there's the polarized PDF. Okay, so the polarized PDF is because we always work with the symmetries for this kind of physics, and then in the case of asymmetries, you would always have the unpolarized PDF in the denominator, right? So of course, since we work with leading order, for example, what we often do, but okay, so for GT they have next to leading order, right? So, and I think JAM they also have their own unpolarized PDF. But the role played by the unpolarized PDF is actually really important, right? So to leading order, next to leading order, we really need to understand what's going on here. And also the rest is, so in that case, that's the dihedron. But if you go to single hadron, you need the fragmentation part, right? So the fragmentation is crucial, and I'm not sure that it's really, no, so yeah. So fragmentation needs to be in the lowest region. So I think what would be important here would be the unpolarized, but then you already know it. But what would be nice is to have it at lower Q values, right?
So this is a two hadron fragmentation function.
Yeah, that's dihedron, but you would have the same kind of behavior for the other symmetries in the case of single hadron. You would just have, so the good thing with dihedron is that you have simple products. In the case of TMDs, you would have convolutions. But instead, you would have the unpolarized. You have the multiplicity, if you like. So the multiplicity will always include the unpolarized PDF. So from a low Q square, right? So that's the thing that can depend on. And then I think that's also why CJ has the fit, and John is also doing this to use it at lower Q values. That's one thing. Yes.
Okay. Other questions, Steve?
So you were talking about single hadron here, and then the challenge, and then you have to know the form factors and fragmentation, things like that. Forget about that. Let's talk jets. Like, what if we just reconstruct dijet or single jet systems to do these inclusive measurements? I mean, wouldn't that be much friendlier from a theoretical point of view anyway?
So you mean jets as opposed to fragmentation?
Yeah.
But I understand there are different functions, right? So
yeah,
and the correlations that you have from the fragmentation function is really related. So that would be from here. So that's part of how can we improve this formalism, right? So there will be this series formalism when you have this fragmentation here coming. So of course you would see jets, but the way it is defined must be slightly different.
Yeah, I mean, on the Athena proto collaboration, a lot of us are just talking about going all in on large radius jets to get as much of the low energy fragmentation as possible to attempt to make the later interpretation back to the Parton level more straightforward. That's a lot of this is going to depend on how much material is or isn't in front of a calorimeter and how we can calibrate the jets and things like that. But that's all part of the plan.
Okay, that's cool. Yeah.
So, and I'm assuming our colleagues over at the competing interaction point are also thinking about some of the same things, right? So, yeah.
Other questions, comments online or? Yeah. Okay. Lucas, maybe you can ask a question. Unmute yourself.
Yeah, I just had a question to kind of shift topics here. Before you talked about like the universality of PDFs up to a certain confidence level, right? I guess out of curiosity, what would be the consequences if we couldn't assume universality of the PDFs?
Okay, so maybe there are two things, and I might have said both things at the same time. Okay, let me go. There was something here. Okay, so there are two things. So we would like to have PDFs that are portables. So you can take them from one process, put them into another process. That's the case of the unpolarized PDF because you have factorization theorems. And in the case of higher twist, they are I think there are such proofs, but they are not to really high order. I'm not sure about that. And so what happens here, for example, for the transversity, they are kind of proof of factorization, but then the point is that since you're not really sure that you can, the first time you do it, the first time you combine the experiments, there's always a doubt that's gonna work, right? And so that's what I wanted to mention about this universality. So before there were like global analysis of this PDF, people checked that they seem to be compatible in some kind of this way, like checking, like reconstructing things. So what would be the consequences if you don't have this universality? Well, it means that we have not understood how to factorize them, right? Perhaps. And the consequences would be that we cannot have global analysis, which would be bad, very bad. Yes. And then there's another thing that I mentioned about universality. Okay, so maybe about, okay, so this one is a different example. So there are fancy twist 3 TMDs, no, twist 2 TMDs that are series function and the Boole model functions. They have a gluon, okay? And they were they match a twist 3 quark-gluon quark function that is a true thermal one. And why is it so important? Is because in that case, because of that gluon interaction that they have, they will depend on the sign of the function will depend on the process. So if you extract those ones from semi-inclusive DIS or from Drelian, you expect to have a different sign. And that's also kind of a proof of universality, right? So all this is universality taken from a different point of view. Did I reply to your question?
Yeah, thank you. That helps a lot more.
Okay.
Okay, I think, well, we had some very good discussion, and I think we are all ready to thank Aurore, and it was a very informative talk, and thank you for coming here and telling us about this interesting physics. And now my understanding is for Wednesday, well, we have some material prepared, but if you have questions, and basically we could go through some of the details of what was shown today, and so please send to me, and I will pass to Aurore. And again, on Wednesday, we'll meet at 3 p.m. in room 202.
Yes, so let me know what you would like me to talk.
Right. So again, we have a flexible agenda for Wednesday. Therefore, again, we could discuss any of these topics in more detail. We can start with this slide. Probably we'll start with these slides and print them out and go through them one by one, and we can stop. And the other thing is that at 2:30 we will meet to congratulate Jing on his PhD defense. So we'll have a coffee and then we'll go upstairs for this recitation. And let's thank also on Wednesday. Yeah. So let's thank Aurore again. And so
thank you.
Yeah.
It was a nice hybrid seminar.
Yes.
So now
okay.
We don't have in person, we have hybrids. Okay. We've had them go less swiftly. That's great. That's wonderful.
Now it's
okay.
No, thank you very much.
Thank you so much.
Oh, no problem. All right, and we're going to shut down for everybody online. So thanks, everyone.